Section 1 Introduction. We're going to talk about a fascinating development in the field of machine learning, specifically in the use of transformer-based models. These models have become the go-to for a variety of applications, including natural language processing and computer vision. But there's more to these models than meets the eye. Recently, it's been found that if you train these large transformers on a massive amount of data, they develop an impressive ability known as in-context learning, ICL. What this means is that once the training is done, these models can tackle new tasks during the inference phase, without any changes to their parameters, by simply taking in a short sequence of labeled examples from a task and then making a prediction for a query example. This ICL ability was first shown by GPT-3, where a model called a CausalLM, a transformer decoder with auto-regressive attention masks, was used. However, subsequent research found that limiting the auto-regressive masks on the entire sequence was too restrictive. As a result, a new model called prefixLM was proposed, which allows full attention within the prefix examples. For instance, in the UL2 paper, the authors combined prefixLM with various types of losses and achieved better performance on various natural language processing tasks. But despite these empirical results, we still don't have a theoretical explanation for the different ICL behaviors of prefixLM and CausalLM. Theoretical studies of ICL are challenging due to the complex nonlinearity of the standard transformer architecture. However, recent work on ICL of linear regression showed that a specially designed parameter construction of a one-layer linear self-attention (LSA) transformer can simulate a single step of gradient descent by using the in-context examples as training data. Furthermore, another recent study used gradient flow to prove that a randomly initialized LSA transformer indeed converges to such a construction during training. Our study continues this line of work and investigates the convergence properties of ICL for both prefixLM and CausalLM multi-layer LSA transformers in the linear regression setting. Here's what we found. 1. We first provide a clear formal proof of the relationship between a multi-layer LSA and multi-step gradient descents in linear regression. 2. We then show that both CausalLM and prefixLM-based multi-layer LSA transformers converge to their respective stationary points with linear rates of convergence. 3. We also show that the stationary point of prefixLM corresponds to the optimal least square solution of the linear regression problem, while the stationary points of CausalLM correspond to the iterative weights of an online gradient descent algorithm with non-decaying step sizes. 4. Interestingly, the stationary points obtained by CausalLM may not become optimal even as the number of in-context examples increases, indicating that CausalLM is not optimal for in-context learning. To validate our theoretical insights, we conducted experiments with LSA transformers as well as ordinary softmax attention-based transformers on various synthetic tasks including linear regression, nonlinear regression, and multiclass classifications. We also compared CausalLM and prefixLM in large language models by fine-tuning POM2 checkpoints on flawn tasks and evaluating them on MMLU 5-shot tasks. Our experimental results support our theoretical findings and consistently show the superiority of prefixLM over CausalLM on ICL. Section Summary. Transformer-based models have become widely used in machine learning applications, and pre-training them on large amounts of data allows them to learn in-context tasks by ingesting a short sequence of labeled examples. While the ICL capability of prefixLM models has been empirically demonstrated, there is no theoretical explanation for their behavior compared to CausalLM models. This paper provides a formal proof of the relationship between multi-layer linear self-attention, LSA, transformers and multi-step gradient descent in linear regression, and shows that both CausalLM and prefixLM models converge to their respective stationary points. Experimental results support the theoretical findings and demonstrate the superiority of prefixLM over CausalLM on in-context learning tasks. Section 2 Background. Let's start by discussing a few types of transformer attention and in-context learning, ICL, as well as a specific transformer structure for linear regression ICL, which will form the basis of our theories. We'll talk about other related work later. Transformers come in several types, including softmax self-attention, SSA, linear self-attention, LSA, causal language models, CausalLM, and prefix language models, prefixLM. When we have a sequence of input vectors, denoted as Z, which is a list of vectors from Z1 to Zn, the output of a standard SSA layer is calculated by adding a certain transformation of Z to each vector Zj in the sequence. This transformation involves several steps, including applying a softmax function, and using 4 different transformations: output projection, P, value transformation, V, key transformation, K, and query transformation, Q. However, because the softmax attention of standard transformers is nonlinear, it's quite complex to analyze theoretically, even for a single layer. That's why many theoretical approaches to analyze transformers have used the LSA layer, which simply removes the softmax function from the attention calculation. In LSA, each vector zj in the sequence is updated by adding a certain transformation of z, similar to SSA, but without the softmax function. This transformation involves summing over all vectors in z, and for each vector z, multiplying it with a certain transformation of zj. This type of attention, where each input vector can attend to all positions, is known as full or bidirectional attention, and is typically used in the transformer encoder. On the other hand, a transformer decoder uses autoregressive attention, where each vector zj is updated by adding a certain transformation of all previous vectors, and itself, in the sequence. This is because the decoder acts as a causal language model, predicting the next vector based on the previously generated ones. The original transformer model includes both a full attention-based encoder and an autoregressive attention-based decoder. However, many studies in natural language processing, NLP, have chosen to use either encoder-only models, like BERT, or decoder-only models, like GPT and POM, depending on the task. This is partly to reduce the number of parameters. Another type of attention, which is somewhere between full and autoregressive, is used when some tasks can benefit from a prefix sequence, such as context or prompt. In this case, the input sequence Z is made up of prefix tokens, which are set up for the task, and sample tokens. The prefixLM model suggests a certain type of attention, where each vector Zj is updated by adding a certain transformation of all previous vectors and all prefix vectors in the sequence. This ensures that each prefix vector can attend to all other prefix vectors. Section Summary. In this section, we review different types of transformer attention and in-context learning, ICL, including softmax self-attention, SSA, linear self-attention, LSA, and autoregressive attention. The original transformer model consists of both a full attention-based encoder and an autoregressive attention-based decoder, but recent NLP research has focused on either encoder-only or decoder-only models to reduce parameter sizes. Another version of attention, called prefixLM, allows prefix tokens to attend to all other prefix tokens, which can be beneficial for certain tasks. Section 2.2 In-Context Learning. We're going to discuss a concept known as in-context learning, which has been covered in various existing literature. In-context learning is about how models can make predictions based on the context they're given during the inference phase. In simpler terms, a model is given a sequence of input label pairs and a query input, and it has to predict the label of the query input using the context examples. Importantly, this is done without changing the model parameters. Next, we'll talk about linear regression in the context of in-context learning. Linear regression is a well-known machine learning problem. The objective here is to find the best weight vector that minimizes the L2 loss, which is a measure of the difference between the predicted and actual values. The gradient of the loss is calculated, and a gradient descent algorithm with a certain step size is used to update the weight vector. The idea of using linear regression to study in-context learning was first suggested in previous work, where the authors proposed a method for training transformers to learn a class of simple predictors, including linear regression. However, they didn't provide any theoretical study. More recently, a concise construction was proposed that shows how a single layer of a certain type of model can effectively implement a single gradient descent step. In this setup, the input is formulated in a certain way, and the parameter matrices are set in a specific manner. The initial weight vector is used in this configuration. It was shown that this setup results in an update of what they call the transform target, and this update is equivalent to the one performed by a single-step gradient descent of linear regression. However, this transform target view seems unnatural to work with. In traditional machine learning, the weight vector or the model prediction is updated, while the actual target remains fixed. Furthermore, their extension from a single-layer model to a multi-layer model is unfortunately unclear. Section Summary. In-context learning refers to models producing context-driven predictions at inference time, where a model is given a sequence of input label pairs and a query input and predicts the label of the query input using the context examples. Linear regression is a classical machine learning problem where the goal is to find an optimal weight vector that minimizes the L2 loss. In recent work, a construction using linear subspace alignment, LSA, was proposed to implement a single gradient descent step for linear regression, but the extension to multi-layer LSA is unclear. Section 3 Multi-layer in-context learner. In this section, we're going to demonstrate that a multi-layer latent semantic analysis, LSA, model behaves in the same way as multi-step gradient descent. We're going to do this by focusing on the weights of the gradient descent and how they relate to the outputs of the multi-layer LSA model. We're going to keep the initial weight at 0 because it simplifies our equations and makes the outputs more meaningful. However, this isn't a requirement, and we'll provide more general propositions for any initial weight in the appendix. Here's our first proposition. If a multi-layer LSA model is built in a certain way and its initial weight is 0, and if its input is formatted in a certain way, then the output of its LTH layer is a combination of the top of the input and the difference between the true label and the LTH updated weight times the input. The LTH updated weight comes from the gradient descent update rule. To prove this, we plug in the initial weight of 0 and the output of the LTH layer into our equations. We find that for all layers greater than 0, the output is equal to the previous output minus a fraction of the sum of the previous differences times the input. Since the first part of the output never changes, we can simplify our equation and focus on the last part, which is the difference between the true label and the predicted label. We then define a new variable that is equal to the true label minus this difference. Rearranging our equations, we find that this new variable is equal to 0 for the initial layer, and for all layers greater than 0, it's equal to the previous value of the new variable plus a fraction of the sum of the differences between the true labels and the previous values of the new variable times the input. Finally, using these equations and the fact that the initial values of the new variable and the weight times the input are both 0, we can prove that for all layers, the new variable is equal to the weight times the input. A full proof is provided in the appendix. In summary, the new variable is exactly the prediction of the LTH gradient descent weights for the input, and the difference is the difference between the true label and the predicted label. Therefore, the new variable serves as a bridge to connect the LSA output and the gradient descent weight. So far, we've only looked at LSA layers with full attention. Next, we'll look at the practical setting of in-context learning, where the input includes not only n in-context training examples, but also an additional test query. We'll focus on two common types of in-context learning, prefixLM and CausalLM, each with a different type of attention. Section Summary. In this section, the authors provide a formal proof that a multi-layer LSA, latent semantic analysis, progresses identically to multi-step gradient descent. They establish a connection between the GD weights and the outputs of the LSA under specific constructions. The authors then discuss the behavior of LSA layers in the context of in-context learning, where the input includes training examples and a test query. They focus on two common variants of in-context learning and their respective types of attention. Section 3.1 prefixLM ICL. In this section, we'll discuss two types of in-context learning ICL models, prefixLM ICL and CausalLM ICL. Starting with prefixLM ICL, this model treats the in-context examples, denoted as Z, as the prefix. It uses full attention on the first n positions, allowing each of them to freely attend to each other. The last query vector, denoted as Z_query, can also attend to any example in Z, but it cannot attend to itself. This is because the query doesn't contain a meaningful label, and if it were to attend to itself, it would include its last dim input as a label, which would contaminate the resulting multi-layer prediction. The updates of the prefix LM-ICL under the same construction follow a certain pattern. The outputs of the LTH layer are represented as delta_J_L equals Y_J, W_L, X_J for each J, and delta_query_L equals W_L, X_query. Here, Y_J represents the true label, W_L represents the weight at the LTH layer, and X_J and X_query are the inputs. Initially, all Y_J_L start as 0 at L equals 0, and gradually approach the true label Y_J as L increases, so that the difference, also as the output, delta_J_L, gradually approaches to 0. At the same time, delta_query_L starts at 0, and gradually approaches to Y_query, the negation of the query label. Next, we have the CausalLM ICL. This model applies autoregressive attention throughout the entire sequence. Therefore, the update rules become a bit more complex. The delta_J_L and Y_J_L are updated according to certain formulas that involve the sum of previous deltas and y's, weighted by the corresponding x's. Moreover, since different delta_J and Y_J are exposed to different ranges of inputs, there is no uniform weight W that is associated with all Y_J. Instead, we define a different weight W_J for each position J, which is updated according to a certain formula. The LTH layer output of a multi-layer CausalLM LSA is represented as Z_J_L equals X_J_top, delta underscore j caret L caret top, where delta underscore j caret L equals y underscore j, w underscore j caret L, x underscore j and w underscore j caret L follow a certain pattern. Similar to prefix LMICL, causal LMICL also has y underscore j caret L equals w underscore j caret L, x underscore j, and delta underscore query caret L equals w underscore n caret L, x underscore query. However, prefix LMICL and causal LMICL are associated with different update rules, and therefore, their outcomes are significantly different. In the next section, we'll look closely into their convergence properties and show why prefix LM is superior to causal LM for in-context learning. Section summary. The prefix LMICL treats the in-context examples as a prefix and uses full attention on the first n positions, gradually approaching the true label as the layer increases. On the other hand, the causal LMICL applies auto-regressive attention throughout the entire sequence, with different update rules for each position, resulting in different outcomes compared to the prefix LMICL. In the next section, the convergence properties of both models are examined, demonstrating why the prefix LM is superior for in-context learning. Section 4. Convergence of the multi-layer in-context learners. In this section, we'll discuss the convergence of multi-layer in-context learners. We'll demonstrate that both multi-layer prefix language models, prefix LM, and causal language models, causal LM, reach their respective stable points as the number of layers increases, and they do so at a linear rate. Moreover, we'll show that the stable point of prefix LM aligns with the least square solution of a linear regression problem, while the stable points of causal LM are equivalent to the iterative weights of online gradient descent in linear regression. First, let's talk about the convergence of the prefix LM in context learner. The computation of a multi-layer prefix LM follows a specific update rule, which means that the outputs of prefix LM layers behave similarly to multi-step gradient descent in a linear regression problem. The convergence properties of such dynamics are well known. In simpler terms, if the weights of the layers follow the iterative updates of this rule, a stable point exists with coefficients that satisfy a certain equation. This equation can be thought of as a product of two vectors, one representing the output and the other representing the input. The iterative weights converge to this stable point at a linear rate. This means that the same stable point is also the stable point of prefix LM, to which it converges at a linear rate. This stable point is exactly the optimal least square solution of the linear regression problem. Next, let's discuss the convergence of the causal LM in context learner. Following a specific update rule, a multi-layer causal LM can be seen as maintaining different weight vectors for each position. We'll show that each position has its own stable point, which appears to be different from the global optimal point of linear regression. Even when the number of in-context samples grows indefinitely, convergence to the global optimal point is not guaranteed. In simpler terms, if the weights at each position follow the iterative updates of this rule, there exist stable points with coefficients that satisfy a certain equation. This equation can be thought of as a product of two vectors, one representing the output and the other representing a matrix of inputs. The coefficients converge to the stable point at a linear rate. This implies that the stable points of causal LM are different from the least square solution of linear regression. A natural question arises: if the position increases, would the stable point ultimately converge to the optimal solution? To answer this, we show that the stable points follow an online gradient descent algorithm. The loss in gradient at each step can be represented by certain equations. Assuming that the stable points are obtained, the next stable point can be calculated by subtracting a certain value from the current stable point. However, online gradient descent is known to converge to an optimal solution only with a decaying step size. Since the step size does not decay in this case, we conclude that causal LM may not converge to the optimal solution even with increasing layers and increasing number of in-context examples. Specifically, in the case of in-context learning, where the number of in-context examples is limited, convergence to the optimal solution cannot be achieved by causal LM. Section summary. In this section, the authors prove that as the number of layers increases, both the multi-layer prefix LM and causal LM converge to their respective stationary points at linear rates. They also show that the stationary point of prefix LM corresponds to the least square solution of the linear regression problem, while the ones corresponding to causal LM are equivalent to the iterative weights of online gradient descent of linear regression. However, they find that even with increasing layers and increasing number of in-context examples, causal LM may not converge to the optimal solution. Section 5. Numerical experiments. In our numerical experiments, we divided our work into three main sections. Firstly, we applied LSA transformers to linear regression problems to validate our theoretical findings. We found that although both CausalLM and prefixLM training errors decrease at the same rate, the test error for CausalLM is significantly higher. This suggests that the stationary solution for CausalLM is not the best one. Secondly, we used standard softmax transformers on a few artificial problems, including linear regression, nonlinear regression, and multiclass classification. We found that our theoretical insights apply to other types of tasks as well, with prefixLM consistently outperforming CausalLM on in-context learning, ICL, in all these scenarios. Lastly, we carried out a few practical ICL experiments using large language models. To directly validate our theories, we first examined in-context learning on a linear regression problem using the LSA transformer. Each input sequence contained 40 in-context examples and 200 queries, with each query attending to all the in-context examples but not to each other. The data input of the sequence was randomly selected from a uniform distribution between -1 and 1, raised to the power of 16. Each sequence was associated with a single weight vector that was randomly selected from a normal distribution with mean 0 and identity matrix as the covariance matrix. The labels were computed as the product of the weight vector and the data input. We evaluated the mean square error between the actual and predicted labels across different layers for both in-context examples and query examples. Our results, averaged over 64 randomly generated sequences, showed that although both prefixLM and CausalLM converge at a linear rate on the in-context examples, the query errors of CausalLM remain above the 0.1 level. In contrast, the query error of prefixLM decreases at the same linear rate as its training error. We also plotted the query errors of the stationary points of CausalLM ICL with an increasing number of in-context examples up to 300. We found that although CausalLM ICL eventually converges to the optimal solution when the mean of the input distribution is 0, it requires more than 100 examples to reach below 0.01. The convergence worsens as we increase the mean of the input distribution, which shows that CausalLM ICL is not the best choice for few-shot ICL. Section Summary. The numerical experiments in this section consist of three parts. Firstly, the authors use LSA transformers on linear regression problems to verify their theorems, showing that the test error of CausalLM is significantly larger than prefixLM, indicating that the stationary solution of CausalLM is not optimal. Secondly, they apply ordinary softmax transformers on synthetic problems and find that prefixLM outperforms CausalLM on ICL in linear regression, nonlinear regression, and multiclass classification tasks. Lastly, they conduct practical ICL experiments using large language models, demonstrating that CausalLM ICL is not optimal for few-shot ICL. Section 5.2 Standard Transformers on Synthetic Tasks. In this section, we're going to delve into the performance of standard transformers on synthetic tasks. We've already shown that our propositions from earlier sections hold true, and now we're going to see if the same can be said for standard softmax transformer-based prefix language models, prefixLM, and causal language models, CausalLM, in incremental context learning, ICL. We're going to test these models on a variety of synthetic tasks, including linear regression, nonlinear regression, and multiclass classification. For these tasks, we used 16-dimensional inputs, with both the input vector x and the weight vector w, drawn from uniform and normal distributions respectively. In the case of nonlinear regression, we applied a sigmoid activation function to the logit, resulting in an output y, that is the sigmoid of the dot product of w and x. For multiclass classification, we generated 3 different weight vectors and assigned labels based on the maximum dot product of w and x. We trained several 24-layer transformers, each with 128 hidden units and 2 heads. We compared the performance of prefixLM and CausalLM, and also looked at transformers with and without shared layers, SL versus UL. The shared layer transformer can be thought of as a recurrent system where the dynamics continue along the layers, and a stationary point may exist given an infinite number of layers. This makes it similar to our previously constructed LSA. Our ICL training dataset contains 64,000 training sequences, each with 40 in-context examples and 20 queries. The queries were independent of each other, similar to the setup in a previous section. We trained the transformers with a batch size of 64 for 100 epochs. More details about the hyperparameters used in these experiments can be found in the appendix. We evaluated the ICL performance using 64 holdout test sequences and reported the test errors on the query examples. The results are summarized in a table. We found that both prefixLM-SL and prefixLM-UL significantly outperformed their CausalLM counterparts in all cases. Interestingly, the shared layer transformer seemed to outperform the unshared layer transformer in classification tasks, suggesting that the latter may be overfitting due to having too many parameters. We also added probes at the output of each shared layer transformer layer to visualize the test errors of intermediate layers. Comparing these figures revealed some similarities. Although the test query errors of CausalLM decayed at roughly the same rate as those of prefixLM in the earlier layers, the decay rate slowed down in the later layers. This could be due to the non-optimal stationary points of CausalLM. These results suggest that the main argument of our paper holds true not just for LSA-based transformers and linear regression, but also for other tasks and models. Section Summary. In this section, the authors verify if standard softmax transformers exhibit similar differences on various synthetic tasks compared to prefixLM and CausalLM ICL. The tasks include linear regression, nonlinear regression, and multiclass classification. The experiments show that both prefixLM-SL and prefixLM-UL outperform their CausalLM counterparts in all cases, indicating the superiority of prefixLM. Additionally, the overparameterization of transformer UL leads to an overfitting problem in classification tasks. Section 5.3 ICL on large language models. We've been examining the performance of in-context learning, ICL, on large language models, specifically comparing the CausalLM and prefixLM models. To do this, we used 3 different sizes of the PaLM-2 language models: Gecko, Otter, and Unicorn. We fine-tuned these models using FLAN, a process that involves over 1,000 tasks. We then evaluated the ICL capabilities of these fine-tuned models on the massive multitask language understanding tasks, using a 5-shot approach. Our findings showed that across all 3 sizes of the PaLM-2 models, prefixLM consistently outperformed CausalLM by more than 3% in accuracy, averaged over the 57 tasks. This supports our theory that the autoregressive nature of CausalLM limits the mutual attentions between the in-context examples, leading to less optimal results. The interest in understanding the mechanics behind in-context learning, ICL, has grown significantly since GPT-3 demonstrated its abilities in various language inference and translation tasks. There are 2 main theories that attempt to explain ICL. The first, the representation theory, suggests that ICL behavior is a topic model that extracts relevant memories based on the context's topic. The second, the algorithmic theory, proposes that large language models learn to implement a learning algorithm and then run it during ICL. Recent studies have found that large language models seem to exhibit certain emergent behavior. For smaller models or data, ICL is memory-based, but for larger models and data, it becomes more algorithm-based. This suggests that both a deep representation memory and a shallow predictor algorithm may contribute to the in-context learning capabilities. The first suggestion to use linear regression to study in-context learning came from a study that found a 12-layer transformer could achieve similar results to a least square solver on a 20-dimension linear regression problem with around 20 in-context examples. This study also found that transformers can learn a few other classes of shallow predictors, including 2-layer ReLU networks. A subsequent study showed that a transformer layer can approximately conduct 4 basic operations: move, multiply, divide, and affine. They combined these operations and showed that a gradient descent step of linear regression can be implemented with a 4-head 8-layer transformer with a number of hidden units proportional to the dimension of the inputs. However, this result only provides a loose upper bound on the model size or depth required for simulating linear regression within a transformer. A more recent work used gradient flow to prove that such matrix constructions can indeed be learned by a transformer. This is why our paper follows this construction and studies its multi-layer convergence properties with different types of attention, prefixLM versus CausalLM.